Hello everyone and welcome to this tutorial on bracing design. My name is Dr. Behzad Mohammed Sadeh. I'm a chartered professional engineer and lecturer registered in Engineers Australia. Today I will guide you through concentric and eccentric bracing system in steel structures. The objectives of this session are simple and clear. First, we all understand the role of bracing in structural systems. Next, we will look at the difference between concentric and eccentric bracing. We will also review key design principles according to Australian standards. Then we will explore load path, member sizing, and connection detailing. Finally, we will work through a simple example to learn about the effects of the bracing. As you can see here, the bracing are mostly come to application to resist lateral loads. What are the major lateral loads considered in structural engineering and design? These are wind, earthquake, blast, vehicle movement, and braking. What are the load impacts? They are result in instability of the structure, sway, they might result in serviceability issues, and finally, they might result in a collapse. As you can see here in this image, showing an unbraced frame. The frame with no bracing system, with no lateral load resisting system, uh, prone to large displacement that finally might put this frame or structure into a collapse risk. While when we go for a brace frame, the amount of the drift or lateral displacement due to these lateral loads is small. So the function of a bracing system is to resist lateral loads through enhancement or enhancing stiffness and stability of the structure. What are the types of the eccentric bracing? Uh, we have different type of the bracing, including eccentric, concentric, and moment resting frame. First of all, we will move on the eccentric VS or versus concentric bracing. For the eccentric bracing, we learn that braces are deliberately offset, as you can see here. This is the offset, while for the concentric bracing, there is no offset, so the braces meet at a single point. What is the advantage of having this offset? It allows energy dissipating during earthquake and providing architectural flexibility. How this energy can dissipate through this offset? This offset is a kind of weak link which imposes large displacement at this location and dissipate lots of energy. While for the concentric bracing, because the bracing meet at a single point, it provides the high amount of the stiffness and they are efficient. Now we will move on concentric bracing to learn more about the concentric bracing. As we already mentioned, concentric bracing systems align the brace forces with the joint center because they meet at a single point, resulting in primarily axial forces in braces. Bracing members meet at a single node, center line of intersection, as we already saw. Load path is direct. Axial force is introduced in braces so that they can resist the lateral load. These provide a very stiff system. And what are the types of concentric bracing? X bracings, V bracings, inverted V or chevron, or K bracing. And what are the characteristics of a concentric bracing? They provide us with high stiffness, It means when we want to have very small displacement, we want to have moderate ductility and also low energy dissipation. These are the characteristics. For example, if we want to design for an earthquake, because of the moderate ductility and low energy dissipation, this option might not be that much interesting. We would better to go for the eccentric bracing. Why? Because through the weak links, they provide lots of energy dissipation and high ductility. Here are the concentric bracing types. As you can see here, this is the diagonal bracing. This is the X bracing. And as you can see here, they meet at a single point by the definition. And this is the inverted V bracing or chevron. This is the V bracing because the shape is like V. And this is the K bracing. And what are the advantages of concentric bracing? As we already learned, they are very stiff, which means the lateral drift or displacement or movement is very limited and small. They are economical because we can use light members through having pure axial forces and simple to fabricate and install. What are the limitations of concentric bracing? Low ductility in seismic zones, as we already mentioned, they are not that much favorable in high seismic zones. Why? Because there is a risk of brace buckling. And the sudden strength loss after brace buckling, which might result in a sudden collapse, it means we have a moderate or low ductility. May obstruct opening and architectural spaces. And we need to check compression, buckling, and tension yielding as per AS4100 and AS1170.4. These are the considerations we need to take through design. We need to consider brace slenderness ratio as well as the for seismic design, allow for post-buckling behavior or choose ductile detailing. The next type of bracing is eccentric bracing. Eccentric bracing systems introduce a deliberate offset, allowing controlled flexural yielding in links for energy dissipation. An eccentric link exists between brace and column or beam. Bracing members do not meet at a same point. So because we have an offset, this offset is a link that has the responsibility of dissipating lots of energy. So it is suitable for a high seismic zone because it provides high energy dissipation capacity as well as introduce high ductility to the structure. Lateral load resisted by axial force and plastic hinge formation in the link, which is mostly favorable to form in beam, not in the column, not also in the connection. X bracing, V bracing, inverted V, and K bracing are type of bracings. And ductile system, which is provided by link, absorbs which provides with the link absorbing seismic energy. The advantages of eccentric bracing are high ductility and energy dissipation, better seismic performance than concentric bracing, and also it allows some architectural flexibility. What are the limitations of an eccentric bracing? Lower stiffness than concentric bracing, requires careful detailing and inspection of the link, higher fabrication cost. And what are the design considerations? Short links, we need to check shear link. Long links, we need to check the flexural yielding. For seismic design, allow for post-buckling behavior or choose ductile detailing. It means that the connection should be such that lots of energy is dissipated and the load path is clear so that the structure is ductile. Also, we need to protect link from brittle fracture by adequate toughness, as we already mentioned about the detailing and connection. And also, it must comply with AS4100, which is the standard for steel structure, and AS1170.4 for seismic provisions. We need to check rotation capacity through the connection, link web stiffening, especially for the beam, because of introduction of this weak link in the beams, the flexural stiffness of the beam affects the bracing system, eccentric bracing system. So it mostly relies on the flexural stiffness of the beam and this link. And another lateral load resisting system that can be used beside the eccentric bracing or concentric bracing is moment resisting frame. A structural system where beams and columns are rigidly connected, allowing the frame to resist lateral forces through bending and shear forces in the members and joints. And bending and stiffness of beam and column connection. This is how the lateral load can be resisted. And no diagonal bracing is required, so it provides open architectural space and full depth and end plate, extended end plate, and haunch connections are the type of bracing. So full depth end plate, extended end plate, haunch connections. And the, these are the types of the moment resisting frame connection. As you can see here, this is the extended end plate. The end plate is extended. This is the haunch connection, and this is the full depth end plate. What are the advantages of moment resisting frame? High ductility and energy dissipation, better seismic performance than concentric bracing, and also allows some architectural flexibility because there is no obstruction to the opening. What are the limitations? Lower stiffness than concentric bracing, requires careful detailing and inspection of the link, and also higher fabrication cost. Design consideration. For the short links, we need to check the shear yielding. For the long links, we need to have the flexural. We need to check the flexural yielding. For seismic design, we need to allow for post-buckling behavior or choose ductile detailing. Also, we need to protect link from brittle fracture. Also, it must comply with AS4100 and AS1170.4 for seismic provisions, including rotation, capacity link, web stiffening. Which one should you choose when you design a structure and designing a lateral load resisting system? Concentric bracings are useful for low seismic zones and high wind areas. Why? Because they provide very rigid frame, which is efficient and economic. Where should we use eccentric bracing? When we have the high seismic zones, because it provides high ductility and for the moderate wind, and it is preferred for the ductility. And when should we use moment resisting frame? When we want to have the architectural flexibility, especially because of the opening, and also when we are at a high seismic zone. It provides high energy dissipation and flexibility for the architectural design. Also, we can use a hybrid or a combination of these main bracing systems. Concentric bracing together with moment resisting frame, or eccentric bracing together with moment resisting frame, which balances the stiffness and ductility. It depends on the designer and the function of the lateral load resisting system. And here you can see a comparison between different lateral load resisting systems. The feature stiffness, when we want to have a higher stiffness, we can choose the concentric bracing, while for the moderate, we can go for the eccentric bracing, and moment resisting frame provide low stiffness. When we talk about ductility, concentric bracings provide low to moderate, while the eccentric bracing and moment resisting frame provide the high ductility. Talking about energy dissipation, as we already mentioned, concentric bracing provides high stiffness but low energy dissipation, while eccentric bracing and moment resisting frames provide the high energy dissipation, so that they are a favorable option for the high seismic zones. Member forces, the concentric bracing introduce axial forces, so it means that the lateral loads are resisted by axial forces introduced in the concentric bracing, while eccentric bracing uh, is the axial plus moment, especially as we already mentioned in the beam, because the function of the eccentric bracing is highly dependent on the flexural resistance of the beam to which the eccentric bracing is connected and the link is introduced. And for the moment resisting frame, the bending is dominant. For the cost, concentric bracing imposes low cost to project, while eccentric bracing has a moderate cost and moment resisting frame cost all the highest amount. And common use, concentric bracings can be used for industrial and tall buildings, while eccentric bracing can be used for seismic zones, and moment resisting frame can be used for high seismic zones where we need architectural freedom. And now we are going to provide you with a simple example to illustrate what is the bracing and how it acts. A steel frame is modeled in SAP 2000 as shown here under. This is an industrial building used as the supporting structure. As you can see here, it is a brace frame. The structure utilizes concentric bracing uh, because we mostly need to have high stiffness to limit the lateral displacement. It provides high stiffness, limits deflections and vibration, and easy to fabricate and install. Concentric bracing includes the K bracing, X bracing, diagonal, and V bracing. Here is the line elements modeled in SAP 2000 to better show how the frame is. This is the unbraced frame. As you can see here, no bracing system is introduced here. And the analysis and design has been conducted in SAP 2000 and showed that the structure is prone to failure and dismember didn't pass because of the lack of the lateral load resisting system. Why? When we introduced the diaphragm as another type of the lateral load resisting system, which we can later in next tutorial talk about the design of the diaphragms, which are flexible and rigid. So this is the roof diaphragm, and these are the diagonal bracing and K bracing, and here is the inverted V or chevron. So different types of bracing are used in these braced structure in order to manage the cost, in order to manage the bracing system. And as you can see here, but the member was passed. And here you can see the deflection of the on-brace frame. And here is the deflection of the brace frame. As you could see here, the amount of deflection is very limited while we're using the bracing system or lateral load resisting system. Now we are going to talk about the connection design. To design the bracing connections to the steel frame, a ramp connection can be used, or you can do the hand calculations, but the majority of the connections are included in the ramp connection. The primary loads are axial loads, including tension and compression. This is the main purpose of the bracing, to introduce tension and compression and raise the lateral forces. Braces are designed to carry lateral load through axial action, forming a triangular truss system within the structure. For tension, the brace must be designed to resist yielding and fracture under tensile forces, while for the compression, this is often the governing case. The brace must be designed to resist buckling, both overall member buckling and local buckling of the cross section. And also we need to check the slenderness ratio, which is the KL over R is the critical parameter here. K is the buckling factor, L is the length, and R is the radius of gyration. The secondary loads are bending moment and shear. So the primary was tension and compression, and the secondary loads are bending moment and shear. Load type axial, and is it required? Yes, always we need to check for that. And when is it most critical? When we design for yield strength and fracture and connection. When we need to check the compression, another axial force, always we need to check because it is a primary. Designed for buckling, global and local, and offer it is a governs the size of the bracing. Bending moment, often we need to check for the eccentric connections, member self-weight, and intermediate load seismic buckling. So we need to check the bending moment. When we need to check the shear, usually we check that for not governing, it is not governing for simple braces, but must be checked, especially when bending is present. Here is another example showing the connection design. As you can see here, this is the chevron bracing inverted V, and this is the connection that we design in RAM. And these are the Australian standards that we checked and used through this tutorial. AS4100 for steel structure, section 6 member capacity, clause 6.2, the general provisions explains how to determine the design capacity of members under different actions, also sets the basis for using limit states design. It means phi multiplied by capacity, which is the factor capacity, should be higher than demand to be on the safe side. Clause 6.3, strength of members in compression, defines buckling strength of compression braces, requires calculating the elastic buckling load and applying slenderness limit. And also it is critical for brace buckling resistance. Clause 6.4, members in tension, uh, it provides a rule for tensile brace strengths, defines how to calculate the design strengths of members in torsion in tension, typically based on yield strength times area, just for appropriate factors. Clause 6.6, member slenderness limit, as we already mentioned, sets the allowable slenderness of member to prevent premature buckling. The slenderness ratio is defined as lambda LE over R. General limit is lambda smaller than 180 for for most structural steel compression members, while for secondary members the limit is higher, is 250 for purlins, girths, bracing not carrying significant load. And section 7 for the connection design, clause 7.2 to 7.6 covers the design rules for bolted and welded connections, showing the joint performs at least as well as the bracing members. And this is the end of this tutorial. If you have any question, please don't hesitate to uh, put your comment under this tutorial video. I would be happy to help you. Good luck everyone and see you soon for the next tutorial.